Hello students, welcome to lecture 2 of p-block elements. In that p-block elements, group 13 elements. This 13th group elements also called third A group. Also they are called boron family. So this group elements are boron. It is a typical non-metal. And aluminium, it is a metal. And gallium, it is almost metal. And indium, it is also almost metal. And thallium, it is also almost metal. And the boron occurs as orthoboric acid H3BO3 and borax in the form of sodium. The formula Na2B4O7 10H2O. And carnite, its formula Na2B4O7 4H2O. And this boron having two isotopes. They are B10, it is 19%, and B11, it is 81%. So the boron having two isotopes B10 and B11. And aluminium is third most abundant element in the earth crust. Aluminium is third most abundant element in the earth crust. And aluminium occurs as bauxite. The formula Al2O3 2H2O. And cryolite, the formula Na3AlF6. And corundum, the corundum formula Al2O3. Next, general characteristics of 13th group elements or third A group elements. The first one, electronic configuration. The 13th group general electronic configuration is NS2NP1. And the elements are boron, aluminium, gallium, indium, and thallium. So the boron atomic number 5 and aluminium 13, gallium 31 and indium 49, thallium 81. And the boron electronic configuration, helium 2s2 2p1 and aluminium neon 3s2 3p1 and gallium argon 3d10 4s2 4p1 and indium krypton 4d10 5s2 5p1 and thallium xenon 4f14 5d10 6s2 6p1. So this is the electronic configuration of 13th or 3rd A group elements. The general outermost electronic configuration of 13th group is NS2NP1. So for boron 2s2 2p1, and next to aluminium 3s2 3p1, and next to gallium 4s2 4p1, indium 5s2 5p1, thallium 6s2 6p1. Next one, atomic radii. If you go from top to bottom in a group, the atomic size increases. Atomic size increases. Hence, the atomic radii increases. But in the group, the atomic radius of gallium is less than the aluminium. So here the atomic radii order is boron, aluminium, gallium, indium, thallium. And the order is boron having less than the aluminium, but aluminium having more than the gallium, and indium having more than the gallium, and thallium having more than the indium. So here the boron 85 picometers and aluminium 143 picometers, gallium 135 picometers, and indium 165 picometers, thallium 170 picometers. So if you go from top to bottom in a group, the atomic radii increases, but here aluminium having more atomic radii than the gallium. The reason is poor shielding or screening effect of d orbitals. Poor shielding or screening. Poor shielding or screening effect of d orbitals. So here I am taking aluminium electronic configuration 1s2, 2s2, 2p6, 3s2, 3p1, and gallium 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p1. So the aluminium having 143 picometers, but gallium having 135 picometers. The gallium having less atomic radii than the aluminium because of poor shielding of d orbitals. So what is the shielding or screening effect? Protecting the outermost orbital electrons from the nuclear charge is called screening or shielding effect. So the shielding or screening effect order is s orbital greater than p orbital greater than d orbital greater than f orbital. So the f orbital having less screening or shielding effect. The shielding or screening effect decreases from s orbital to f orbital. S having more shielding and f having less shielding. So if I take gallium, so this is the nucleus of gallium, and outermost orbitals are 4s and 4p, and before that orbitals we have 3d orbital, and after that we have 4s and 4p. So in this orbit we have 4s and 4p, and in this orbit we have 3d orbitals. So that 3d orbitals having less shielding or screening effect. Due to that 4s and 4p electrons are strongly attracted towards the nucleus. Due to that the gallium atomic size will decrease. Consequently, atomic radii decreases. So that gallium having less atomic radii than the aluminium. Next to ionization enthalpy. Generally, if you go from top to bottom in a group, the ionization enthalpy decreases. But in 13th group, the ionization enthalpy first decrease, then increase due to poor shielding or screening effect of d and f orbitals. So the ionization enthalpy order is boron having more than aluminium, then aluminium having less than gallium, and the gallium indium are having approximately same, and that indium having less than the thallium. So this is the ionization enthalpy order in 13th group. So first the ionization enthalpy decrease, then ionization enthalpy increase, and the first ionization enthalpy is less than the second ionization enthalpy, and second ionization enthalpy is less than the third ionization enthalpy. So the first IE1 is less than IE2 is less than IE3. The first ionization enthalpy is less than the second one, and second ionization enthalpy is less than the third ionization enthalpy. The general outermost electronic configuration is NS2 NP1. So first ionization enthalpy means the electron removed from p orbital. So here the less energy is required to remove the electron from p orbital. And next, after removing that electron, then we have NS2 NP0. Next electron removed from s orbital. So here the energy required to remove the electron from s orbital is called second ionization enthalpy. So here first ionization enthalpy, and here second ionization enthalpy. After removing the electron from s orbital, then we have NS1 NP0. So here this electron is strongly attracted towards the nucleus. So here more energy required to remove the electron from s orbital. So here to remove this electron, the energy required, that energy is third ionization enthalpy. For example, if I take aluminium, so here I am taking the aluminium Al. If you remove one electron from aluminium, then we are getting Al plus. So this is called first ionization enthalpy. And next, and here more energy required to remove the electron from monopositive ion, and here the energy is second ionization energy or second ionization enthalpy. Then we'll get Al plus 2, and here much more energy required to remove the electron from dipositive ion. So here the energy required, that energy is called third ionization enthalpy. Then we'll get Al plus 3. So first ionization enthalpy is less than the second one, and second one is less than the third one. And the ionization enthalpy of third A group, means 13th group, is less than ionization enthalpy of second A group, due to electron removed from p orbital in 13th group and electron removed from s orbital in second group. For example, I am taking third A or 13th A group. Boron, and second A beryllium. And here boron electronic configuration 1s2, 2s2 and 2p1, and beryllium 1s2, 2s2. So in 13th group we are remove the electron from p orbital, and here in this second group we remove the electron from s orbital. So the ionization enthalpy of third A group is less than the ionization enthalpy of second A group. Next one, electronegativity. If you go from top to bottom in a group, the electronegativity first decreases from boron to aluminum. The electronegativity decreases, then increases from aluminum to thallium. Electronegativity increases. So boron to aluminum, the electronegativity decreases. Then aluminum to thallium, electronegativity increases. And boron family electronegativity means third A group electronegativity is more than the S block elements electronegativity. So boron to aluminum, the size increases and electronegativity decreases, and aluminum to thallium, size decreases and electronegativity increases. Next, physical properties of 13th or 3rd A group elements. That boron is a non-metallic in nature. Non-metallic. And it is a black colored solid, and it is very hard, and it has high melting point and boiling points. Melting point and boiling points are high. The remaining elements in boron family are soft metals. Soft metals. They have low melting point and boiling points. Low melting point and boiling points. They have high electrical conductivity. And gallium have low melting point, that is 303 Kelvin. In summer, that gallium may exist in liquid form, and it has high boiling point, that is the boiling point is 2676 Kelvin. The gallium having high boiling point, that is 2676 Kelvin. And gallium is useful material to measure the high temperature. The gallium is useful material to measure the high temperature. And the density increases from boron to thallium. Density increases. From boron to thallium, the density increases. Next to chemical properties, oxidation state and trends in chemical reactivity. So we know that the boron having small size. Due to that small size, the sum of its first three ionization enthalpies is very high. Means the sum of IE1 and IE2 and IE3 is very high. Consequently, the boron prevent to form +3 oxidation state. Means it is not able to form boron +3 because it is very difficult to remove the 3 electrons from outer shell of that boron to get the boron +3. So that boron can form covalent compounds. Boron can form covalent compounds with 3 covalent bonds. And if you go from boron to aluminium, the ionization enthalpy decreases because size increases. So the ionization enthalpy decreases. So that aluminium can form Al+3 ion. Because the aluminium size is more than the boron. So we can easily remove the 3 electrons from outer shell of that aluminium to get the Al+3. And the gallium, indium, thallium or can form +1 and +3 oxidation states. In gallium and indium, the +3 oxidation state is very common. So that gallium, indium, thallium or can form +1 and +3 oxidation states. In gallium and indium, the +3 oxidation state is very common. But in thallium, +1 oxidation state is more stable than +3 oxidation state due to very poor shielding effect of f orbitals, and the +1 oxidation state stability Al less than gallium less than indium less than thallium. So in thallium the +1 oxidation state is more stable, and in trivalent state boron has 6 electrons around it to achieve the stable electronic configuration. So it accepts a lone pair to get the stability. Then here the boron act as a Lewis acid. For example, I am taking BF3 and BCl3. So here BCl3 easily accepts a lone pair of electron from NH3. So here I am taking boron and 3 chlorines, and there is a empty orbitals in boron, and it accepts a electron pair from the NH3. So we know that the boron atomic number 5, electronic configuration 1s2, 2s2 and 2p1. So in p orbital there is a 1 electron, so there are empty orbitals. So that empty orbitals receive the electron pairs from the electron donors. So here that boron accept the electron pairs from the NH3. So then it can form tetrahedral compound of BCl3 NH3. So here 3 chlorines, covalent bonds, and 1 NH3 with coordinate covalent bond. So its geometry is tetrahedral, and here its geometry is trigonal planar. And AlCl3 get stability by formation of dimer. So that AlCl3 dimer is this one. So here 3 chlorines and here also 3 chlorines, and this chlorine can donate the electron pair to the aluminum of another molecule, and this chlorine also can donate the electron pairs to the aluminum of another molecule. So it is a dimer of AlCl3 and its geometry is tetrahedral. So AlCl3 is a more stable in dimer form. So here the bond length between the chlorine and aluminum is 206 picometer, and the bond angle, so here the bond angle is 101 degrees, and here the bond angle is 79 degrees, and here the bond angle is 118 degrees. And AlCl3 react with water to form octahedral complex. So AlCl3 plus water, 6 moles of water, then it can form AlH2O taken 6 times, and here plus 3 Cl minus. Next one, reactivity towards air. The boron is unreactive in crystalline form. The boron is unreactive in crystalline form. And aluminium forms thin oxidation layer on the surface. The aluminium can form thin oxidation layer. Thin oxidation layer. And amorphous form of boron and aluminium on heating react with air. Amorphous form of boron and aluminium on heating react with air to form B2O3 and Al2O3, and with N2 at high temperature they can form nitrides. So here E is the element of 13th group. It is a solid, react with air O2, gives rise to, on heating, E2O3. It is also solid. This is with air, and with N2 element react with N2 on heating, it will give nitride. E means element. So here let me take 2 and here also 2. So the 13th group elements with oxygen, they can give E2O3, and the 13th group elements react with nitrogen, they can give nitrides. And B2O3 is acidic and it react with basic oxides, then form borates. And aluminium gallium oxides are amphoteric. They can react with acids and bases. That aluminium and gallium oxides are amphoteric and they can react with acids and bases. And indium thallium are basic. then they can react with acids. And next, reactivity towards acids and bases. The boron does not react with dilute acids and bases. Does not react with dilute acids and bases. And aluminium shows amphoteric character and it reacts with mineral acids and bases. The aluminium shows amphoteric nature and it reacts with mineral acids and bases. Means it reacts with acids and bases. And aluminium react with dilute HCl and it liberate H2 gas. So aluminium solid react with dilute HCl aqueous gives rise to Al plus 3 plus Cl minus plus H2 gas. It is aqueous and it is also aqueous. So here 2 and let me take here 2 and here 6 and here also 6, then here 3. Now it is a balanced equation. And the concentrated HNO3 protect the aluminium from oxide layer, and aluminium react with aqueous base, then it liberate H2 gas. Aluminium react with aqueous base, then it liberate H2 gas. Let me take the reaction. Al solid plus NaOH aqueous plus H2O liquid gives rise to, it will give sodium tetrahydroxoaluminate complex. Na plus AlOH taken 4 times and here minus. It is aqueous plus H2 gas and balance that equation. Here 2, 2, 6, 2 and here 3. Now it is a balanced equation. So that aluminium react with aqueous base, then it liberate H2 gas. Next, reactivity towards halogens. So that 13th group elements react with halogens to form trihalides except thallium I3. So E is the 13th group element. That 13th group element react with halogen X2 gives rise to EX3. So here X nothing but fluorine, chlorine, bromine and iodine, and E nothing but 13th group elements: boron, aluminium, gallium, indium, thallium. So it is a solid and it is a gas and it is also solid, and balance that equation. So here 2 and 3, then here 2. So the 13th group elements react with halogens to give the trihalides. Next one, important trends and anomalous properties of boron. The trichlorides, bromides and iodides of 13th group elements are covalent in nature. Trichlorides, ECl3, E means 13th group element, and tribromides and triiodides of all 13th group elements are covalent in nature, and halides of 13th group elements are react with water, then they can form tetrahedral and octahedral complexes. So halides of 13th group elements react with water, then they can form tetrahedral, MOH taken 4 times, tetrahedral complexes and octahedral complexes, MH2O taken 6 times plus 3, except boron. Except boron, all the 13th group elements, they can form tetrahedral and octahedral complexes with the water. And the monomeric trihalides are electron deficient and they are strong Lewis acids, means they can accept the electron pairs. For example, BF3 easily react with Lewis base of NH3. So here, to complete the octet around the boron, that boron accept the electrons. So this BF3 react with NH3. So around that boron we have only 6 electrons. See here, 3 fluorines are there. So each bond 2 electrons, 2 plus 2 plus 2, total 6 electrons. So to complete the octet, it required more 2 electrons. So that boron having empty orbitals, so that empty orbitals accept the electrons from the electron donors. So that NH3 can donate the electron pair. Now the boron having 8 electrons around it. So then it can form BF3 and coordinate covalent bond NH3. So the monomeric trihalides are electron deficient and they are strong Lewis acids. They can accept the electrons, and the maximum covalence of boron is 4. Covalence of boron is 4, and AlCl3 complete the octet by dimerize. So that AlCl3 dimer form is this one. And here the chlorine act as a bridge. So the chlorine can donate the electron pairs to the aluminum of other molecule, and here this chlorine also donate the electron pairs to the aluminum of other molecule. So these chlorines are act as a bridge, and the aluminiums accept the electrons from the chlorine. So this aluminium accept the electrons from this chlorine, and this aluminium accept the electrons from this chlorine. So the AlCl3 complete the octet by dimerize. So here there are 8 electrons around that aluminium, 2 plus 2 plus 2 plus 2, total 8 electrons, and here also 8 electrons around that aluminium.